Scientists use buffer solutions all the time when we are doing experiments, especially with living organisms that need a particular pH to thrive. But nature uses buffer solutions all over the place when it needs to stabilize a particular pH because it's the most appropriate one for whatever process it happens. For example, you have what we call the phosphate buffer, which is between dihydrogen phosphate and hydrogen phosphate, and it's in the cytoplasm of the cells. And if hydrogen ions enter the cell through the cell walls, then they will react with the hydrogen phosphate. And if hydroxyl ions were to enter the cell, then they will react with the dihydrogen phosphate. So then you have a species, a basic species that can react with acids entering the cell, and you have an acidic species that can react with bases entering the cell, like the hydroxyl, and then you keep the pH of the cytoplasms at appropriate levels without whatever hydrogen whatever acidic or basic species enter the cell walls. And cellular fluid in mammals has a pH of between 6.9 and 7.4, and that pH is maintained within these ranges by these phosphate buffers between dihydrogen and hydrogen phosphate. Another example of a very successful use of a buffer solution is the carbonate buffer. Blood plasma keeps the pH in partly because of this hydrogen carbonate, dihydrogen carbonate system, what we call the bicarbonate system, because the old way of calling hydrogen carbonate HCO3 minus is bicarbonate, and it's a very common name and it still keeps kicking around. So this blood plasma buffer, this bicarbonate system is composed of carbonic acid, H2CO3, and hydrogen carbonate, HCO3 minus. So if you have an excess of acid in the blood plasma, then it reacts with the hydrogen carbonate. If you have, this is the basic species, if you have an excess of base, an excess of hydroxyl ions, then it will react with the carbonic acid, with the acidic species. If you had the same amount of hydrogen carbonate and carbonic acid, then the pH of the blood would be 6.1, because that's the pKa of that reaction. But nature plays with the ratio of the hydrogen carbonate and carbonic acid, a ratio of 20:1, to maintain the specific pH of blood, which is 7.4. Carbonic acid and carbonate buffers are hugely important, not only, for example, to regulate the pH of the blood, but also in an environmental context. And this is a slide in which shows how the different forms of carbon, as CO2 gas, CO2 dissolved in water, CO2 reacting with the water to form this carbonic acid, and then having this acid-base equilibria and forming the hydrogen carbonate and the carbonate, and maybe reacting with other ions in solution to form a soluble salt like calcium carbonate that might, if you make enough, will precipitate and you will have solid sodium carbonate. All these regulate the acidity of seawater. So all these processes of the CO2 becoming carbonic acid, hydrogen carbonate, and carbonate reacting with calcium 2+, and the process of then, if you create too much calcium carbonate, the calcium carbonate precipitating from solution and forming a solid, helps nature regulate the acidity of water in seas and oceans. And finally, a little bit of environmental chemistry. How does the increase of atmospheric CO2 because of climate change would affect the acidity of the oceans? Well, this is the level of atmospheric CO2 measuring Hawaii, the Mauna Loa Observatory, since the 60s to the 2020, give or take, and how it has been increased over the last 50, 70 years. How does this affect the acidity of oceans and sea, the acidity of our oceans? Well, the line in the red, so here at the bottom you've got years between 1958 and 2018. On the left hand side you have concentration of CO2 in the atmosphere, and on the right hand side you have the pH of the ocean. So the red line indicates the concentration of CO2 in the atmosphere, which has been increased over the last few decades. In green, this green line indicates the concentration of CO2 in ocean waters. And as you can see, the blue line represents the pH of oceans. So as the concentration of CO2 in the atmosphere increases, more CO2 enters the oceans, in that equilibrium I showed you in a previous slide. And the more CO2 that you have in the ocean, because it's an acidic species that will create carbonic acid and then will liberate hydrogen ions, the lower the pH, the more acidic it becomes. So this is all. I hope that the different videos will help you understand a little bit better what is an acid, what's a base, the concept of pH and why we care about pH, a little bit about how different salts are soluble at different temperatures and in different quantities, and how pH can affect that the solubility of many salts, and what a buffer solution is. Why we care about buffer solutions, how to make them, and how we humans and nature use them to regulate different processes. And also the use of the pH diagrams that you may or may not have understood how they are made, but that are very useful tools that allows us to measure the pH of a particular solution, and then that gives us an indication of the different species of a particular element that you have in that solution and what proportions they are going to be, just by taking that measurement, the pH measurement. And this is all from me. Thank you for watching.